Okay, welcome to EE222. We are okay, so let's go down to week 8. We are going to finish off today in EE222. We are on week 8 lecture 3, week 8 lecture 3 here. And just note that if you are following some videos from last year, you may get confused because in 2019 and 2020, 2018, 2019, 2020, 2021, all the way up till this year, we used to have 14 weeks per semester, but this year in 2022, it's going to be 13 weeks, right? So we're going to move at a faster pace, right? All right, okay, so we were looking at 4 particular types of devices. Firstly, we looked at something called a multiplexer. What is the multiplexer? There is a data line, there are select lines, there are 3 sets of lines. Firstly, there is a data line, there is a select lines, and then there is the output line, single output, right? So multiplexer, using the select lines, you choose which data line gets connected to the output, right? Simple concept, right? Okay, there is multiplexer, and for each of those, you have to know how you will derive the Boolean or basic Boolean algebra. Demultiplexer is the opposite of multiplexer. What does it do? You have one data line, you have multiple outputs, right? And you choose, using the select line, where the data will be directed to, whether it will be directed to output number 1 or output number 2, all right? Okay, so multiple outputs in this case. In multiplexer, there was single output. Demultiplexer, exact opposite, you're flipping it around. Then there was decoder. Decoder, only 2 sets of lines. One is the address lines, and one are the output lines. So using the address lines, you select one of the outputs which will go high or low depending on if there is a bubble, right? Okay, so the address lines, based on that address, determines which particular output will go high, and obviously the other outputs will go low. All right, okay, now sometimes we introduce the bubble, right? So if there is a bubble, it works the other way around. So everything is high except for the selected line will be low. All right, so that's how the bubble works. Right, so you should know which one to use. All right, so there we are, and I gave you guys some homework. I said for this one here, so 74LS138, 3 by 8, please look at the naming convention. For 3 by 8, what is the, you know, you have to draw the truth table, right? Obviously, there's going to be 3 inputs, 3 columns of inputs, 8 columns of outputs, 8 possible outputs, so 8 columns, right? And because there's 3 inputs, how many possible rows, guys? 8 rows, all right? 8 rows, 2 to the power of 3. Where did we get the 8 outputs from? Well, you look at the chip, look at the system. The system has got 8 outputs. So you then populate the truth table. From there, for each line of output, you will get a different equation. So you'll get 8 circuits. Okay? Now, there's another chip known as the BCD to 7-segment decoder. Again, it's a decoder, right? So when you look at your calculator, if you've got a FX82 calculator, right, you see if you look at the screen, you know, if you type the number 8 or number 5 or number 7, it's a particular pattern. So this pattern is called a 7-segment. You see that pattern in red? That's called a 7-segment display, and that's also used in your FX82 calculator if you use a FX82 calculator. So that's a 7-segment display. These 7 segments are labeled A, B, C, D, E, F, G. Now, and you've done this in your tutorial, I believe. It was question 4 in your tutorial, right? So based on your code over here, so let's say if you have 0011, right? That will be the number 0011 translates to number 3. So 3. How do we light up 3? It will be A, B, C, D and G. What will be happening to F and E? It will be off. So number 3, 0011, A is 1, B is 1, C is 1, D is 1, G is 1, but E and F will be 0. So in that particular way, that is your truth table. We then come up with how many outputs, guys? How many outputs? 7. 1, 2, 3, 4, 5, 6, 7. So we come up with 7 different outputs. So same concept is applied. And you've done this in the tutorial. Usually, if you look at it, every 7-segment display, there is a decimal point over here as well. So that usually becomes the eighth output. All right? Okay, so the concepts are the same, only we are applying it. Right? So this is an important one. That's why we gave it in the tutorial. Right, so let's have a look at the tutorial. There we go. That's your tutorial. And you probably had a look at this particular 7-segment display. And how is the 7-segment display built? Well, it's basically a bunch of 7 LEDs. In fact, there is a decimal point over here, so I've showed it to you. Right? So that's the circuitry. And if you're doing EE212, you'll be able to gather what's happening over here. All right? So please make sure you attempt this particular tutorial. And, you know, usually in the tutorial sheet, there's lots and lots of problems. And it's not going to fit in 1 hour. But you're expected to do things before you go into the tutorial so that you can finish it off and just, you know, get your difficult questions checked. And this is one of the most important ones. All right? Okay. Now, let's have a look at further topics, guys. There's a chip for that, right? The 74LS47. All right, there we go. That's the same thing, the chip. All right, then there was encoders. Right, remember I was talking about decoders? Encoders is exactly the opposite. Just like multiplexer and demultiplexer are opposites of each other, encoders and decoders. So decoders, you supply, right? You supply a particular bit pattern. You make one particular pattern high or low. Right? From this 4 over here, you make one of them high or one of them low, and, right? Sorry. So because there's a bubble over here, remember, if there's a bubble. So whenever you see a bubble, what does the bubble stand for? The bubble means that it operates on logic low. That means everything is usually high, and the selected line is the one which is low. If there is no bubble, everything is low and one of it is high. Remember that? So the bubble means that the selected line has to be made low. Remember that. All right? So if you are confused, please go back to Tuesday's lecture and then work backwards. So if, let's say, if D3 is low, then A0 and A1 will be 1, 1. It's the exact opposite of decoder. Encoder means you supply it with one line and it will generate the binary for you. Of course, once again, what do? We build this using the truth table, and then, you know, we get the equations and so forth. So by now you would have been familiar with it. All right. Now let's have a look at have a look at some applications, guys. Some applications. Now, if you remember earlier on when we did some applications, some basic applications. Let me just scroll up over here, and really I'm not writing things over here today because it's, you know, we've got all of this. But remember we said, hey, if we have there we are. Okay, so I said one of the applications of a multiplexer is what? One of the applications of a multiplexer is you can be given a sum of min-term function, and you can use just one multiplexer chip to represent them. Okay, everyone okay with that? All right, now let's now take it further. Then we said, okay, in the same way, if your multiplexer chip has got few select lines, you can use one of the lines here to represent an equation. Okay, so that was with regards to multiplexer. All right, now let's have a look at another application. Another application with regards to our Boolean algebra is over here. So just remember the 4 different special circuits which we've learned. Actually it's 5. The first one was multiplexer, exact opposite is demultiplexer. Then number 3 is decoder, the exact opposite is encoder. Now one special category of decoder is the BCD to 7 segment display. There is one special category. So it's like number 5. Alright? Okay. Now another function. You can use a mux to build some basic logic gates. So let us say you walk into the lab and you ask for an AND gate as shown, and the technician says, sorry, we're out of AND gates, and you can always say, okay, I want to build it. What's one option? You can build an AND gate using NAND obviously, or you can build it using NOR, but you can also build it using a mux, right? And that's how we do it, right? That's how we do it. Simple circuit that doesn't need explanation. I'm just going to give you a minute to have a look at the truth table over there, right? Remember these are select lines, 0, 0. Of course, what have we done over there with the data line? What did we do? We take our data lines and we make it look like the outputs of an AND gate. But doesn't that correlate with what we spoke about earlier on? Any mux can be used to represent a sum of product system, right? A sum of product system or a sum of minterm system. So basically what we did over here is, this is a sum of minterms system. So we just place the outputs into this over here, and that 4x1 mux will then start to act like an AND gate. Right? But what is the condition? The inputs have got to be fed in. All right? Okay, so that's a 2-input AND gate. Right, okay, we've done this one here. Everyone remembers this one? We did this problem early on. So same thing goes over here. We can represent any sum of minterm function using a multiplexer. Now, in your tutorial next week, you will see that we can build bigger multiplexers using smaller multiplexers. All right, but we're not doing that now. In today's lecture, we are doing just this much. All right, okay, now, so this I've already explained in yesterday's lecture. All right, now let's have a look over here. Another application of decoder. We are talking about decoder now. Decoder. All right. Now you can build an AND gate. I just spoke. How many ways is there which we can build an AND gate? Firstly, so let's say you go to the technician, and the technician says, or the shop says, sorry, no AND gate because of the war in Europe. There is a shortage of AND gates. All right, so what do? You say, all right, first thing you're going to ask, do you have an AND gate? Okay, because you can build an AND gate using NAND gates. That, right? And he says, sorry, no NAND gates. Then what do? Or they says, we got NAND gates, but it's used already booked by some other students in 4th year. Then you're going to ask for NOR gates, because you can build an AND gate using NOR gate. Right? Let's say there's no NOR gate, or the NOR gate was damaged. Then what do? You say, do you have a 4x1 mux? Right? You can build it using a 4x1 mux, and I just showed you. And he says, no 4x1 mux. Then what do? You can build it using a 2x4 decoder. Right? You can build it. So what I'm trying to show here, you'll always have multiple pathways to achieve that problem. All right? Okay? So you have a 2x4 decoder. What does the 2x4 decoder mean? Which means there are 2 address lines and 4 output lines. Right? 4 output lines. Once again, what does decoder mean? 2x4, the 2 stands for number of addresses, by 4. 4 means the number of possible outputs. Alright, now, have a look at this decoder over here, that bubble. Can somebody tell me, alright, if there was no bubble, what would happen if there was no bubble? No bubble, right, on the outputs. If there was no bubble, What would happen if we select two address lines? What would happen if we select two address lines? Let's say we select 1, 1. What would happen? Come on guys, quickly. Output number 3 will go high or low? It will go high, everything else will remain low. Now, because there is now a bubble, let us now consider the scenario of the bubble. If we select address 1, 1, x is 1, y is 1. What will happen to output 3? Now there is a bubble. Output 3 will be low, everything else will be high. All right, now, okay, so let us look at this particular thing. We do it such that you want to build an AND gate, right? So when input is 0, 0, when input is 0, 0, which line will get selected? Which line will get selected, guys? Line 0 will get selected, but because there's a bubble there, line 0 will stay on 0, everything else will become 1, thereby 0, 1, 1 will give you output of 0, 0. All right? Now, 0, 1, 0, 1, over here, 0, 1, second row, 0, 1, which output will become low? Output 1 will become low. Everything else will become high. So 1, 0, 1. Z will remain at 0. Now 1, 0. 1, 0. Output 2 will become low. Output 0 and output 1 will stay high. So 1, 1, 0 going into an AND gate, 1 and 0 will give you output of Z will equal to 0. So you'll stay at 0. Do you see how we have designed this? Right? And notice how output 3 is never used. Output 3 is because you never need output 3. Output 3 only comes alive if you have 1 and 1. Alright? So if you have 1 and 1, okay, let's consider the last scenario. 1 and 1, output 3 will become low, everything else will be high. 1, 1, 1. Going into an AND gate, Z will give you 1. So that's how we built an AND gate using thing. All right? And sometimes, guys, for the purpose of exam, we will say in this particular thing, can you please use a decoder to implement the following? We will ask you the question in that particular manner. Right? Implement the following circuit using decoders only. All right? Okay, let's have a look at the next particular application. All right? So this is another decoder. Okay, this is another decoder. A decoder, this is 74LS138. Right? 74LS138. Let me just show you, where did we discuss that 74LS138? It's all the way over here. It's a 3 by 8 decoder. So 3 address lines, 8 output lines. Right? 3 address lines, 8 output lines. Okay. Right. So you can use a decoder. What can you use a multiplexer for? You can use it to represent a sum of products. But also you can use it to represent a sum of product of next terms as well. Remember, we did that problem yesterday. You just look at the other way around, right? Okay, now in this case here, the question says to use a decoder, right? So you've been given the product of next terms, and those addresses 2, 3, 5, and 6. What does that address refer to? 2, 3, 5, and 6. Locations of all the zeros, the addresses of all the zeros. So 0 will occur at address 2, 010, address 3, 011, address 5, 101, and address 6, 110. Right? So what do we have here? So if you look at it, we take all the addresses where the zeros occur, okay, and you end it. You end all the zeros, right? You end all the zeros. So there were 4 zeros, and we end those 4 zeros. Okay, so you can go through this truth table. All right, now, so you guys are familiar with A, B, and C. A, B, and C is the particular addresses, right? The address lines. Over here, Y0 till Y7 is the output lines, but remember there's a bubble. Always remember there's a bubble. All right. Now you may be wondering, what is this thing here? Well, those are like the activate lines or enable lines. Lines which we don't necessarily control all the time, but these come in handy if you want to toggle, if you want to combine, let's take it one step further. You want to build a 3 to 8 decoder, but all the technician has is lots of 2 by 4 decoders. So these lines here, what you call the control lines. So these are your address lines, these are your output lines, these here are your control lines. So enable, disable, things like that. All right? Okay, and you'll do that in your tutorial next week. So basically, when you have G1 is enabled, then this particular chip turns on. All right, guys, that's it for encoders and decoders. So let's just switch over to the camera now. I'm just going to note down what was the, I'm just going to note down, so that was Lecture 2, Week 8 was yesterday. What date was it yesterday, guys? 18th? Was yesterday 18th? So we did multiplexer, we did demux, we did encoder, we did decoder, right? So because yesterday my system wasn't working, the camera wasn't working. Lecture 8, and today is the 19th, am I correct? So we did 7 segment, oh sorry guys, BCD to 7 segment decoder. We did, what else did we do, guys? So AND gate from mux, AND gate from decoder, what else, guys? We did sum of products and product of sums using decoder and or mux. All right, now let's do one problem, guys. Let's do a problem, very simple problem. Can you guys quickly do this one? using a decoder. I'll give you guys 2 minutes. You can talk with your neighbor. Okay, you can discuss with your neighbor or your friend. So, firstly, the sum of minterms. What do those addresses point to? What do those addresses point to? They point to the locations of all the ones. All right? Okay, fair enough. And if you want to use a decoder, which decoder would you use in this particular scenario? Which decoder? So we'll use a 3x8 decoder. We'll use a 3x8 decoder, right? Okay. And because it specifically says use the decoder, right? If we were to use a mux, it's very easy, right? Now, together with the decoder, what else would you need? A decoder alone won't be able to fix your problem. What else do you need? You need a AND gate. So a decoder alone will not be able to do your problem. So okay, maybe I put it like this, using number 1 and part 2 mux. So for mux, okay, so for decoder, for number 1 you will need a 3x8 decoder, right? You will also need AND gate. We will also need AND gate. All right? So the way you're going to do it is, have a look here. Let's have a look at the problem over here. In this particular problem, it was product of max terms, right? Product of max terms. So the locations of all the zeros, right? So notice how the zeros were ended together. So what are you going to do? You're going to identify, let's come back to our problem over here. You're going to identify the locations of all the zeros. All right? And then how many input AND gate will you need, guys? If there's 4 ones, how many zeros will there be? There will be 4 zeros. So you need 4 input AND gate. Right? So what do? You'll have your decoder here. Right? I'm just going to do a rough sketch, but I expect you, in your free time, you draw it neatly. And wherever the ones are located, guys, wherever the ones are located, wherever the zeros are located, where will be the zeros located? Okay, so let's see this. 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, and then you have 3 inputs over here. All right? Now, you look for wherever your zeros are. Where are your zeros are located, guys? Can you tell me where the zeros are located? 0, address 3, 5, 6. So 0, 3, 5, 6. And then you will put an AND gate. That's how you do it. You put an AND gate. Simple as that. Okay? So you look for the zeros. Oh, one mistake. What mistake have I made over here? can you notice something in my chip, my 3x8 chip? The bubbles are missing. The bubbles are missing, right? The bubbles are missing. Guys, I want you to take a note over here that you can also use an OR gate. In some scenarios, you can also use an OR gate, the other way around. You can use an OR gate if the bubbles are not present, right? So I want you to take a note over there, and because in your exam or in your short test or quiz, I will definitely be giving you problems like this, that you have to use OR gate, the bubble is missing, I will say the bubble is missing, or the bubble is present. So, or I'll give you the picture of the chip, and from that you have to know what to do, right? Okay, so the bubbles are missing. Right, so please, if you could place the bubbles there. All right. Okay. So let's have a look at the PC again. Notice over here, guys. Can you notice the address lines in which order they have been done? Right. The order. If you look at the decoder. Have a look at the address lines, A0, A1, A2. Now, can you tell me what is the most significant bit here? A2, right? A2 is the most significant bit. What is the what is the most significant address bit? It will be A2. A0 is your least significant address bit. Okay? So A2 is your most significant. How do we know most significant? Well, you have a look over here. When you do your truth table, you see that A2 is your most significant. Your least significant address bit is A0. So I want you to note that. All right? Okay. Now, if you come down, look at the CBA, right? Okay, so they've labeled their chip ABC. This is the labeling on the chip Y0, Y7. These are some labels on the chip. But I want you to note where your ABC, the ABC from your thing is coming in. So the notes are slightly confusing. There are two sets of ABC. One is the ABC labeled on the chip numbers, whatever's written on the chip. Then there's your ABC coming in from your function. If you look at your function, there is an ABC in your function. So please take note of what's happening over there. Right? Okay. Now, in your free time, I want you to, how many of you have got, were able to get a copy of Circuit Maker and have a Circuit Maker sitting on your computer? Right? Now, I want you to, in your free time as homework, play with the decoder and the encoder. All right? So write down the homework. Right? Experiment with the encoder and decoder on Circuit Maker. All right? Just in your free time. Because obviously you get lab only once a week, 3 hours to play with the chip. But the good news about this particular course is whatever is happening on software is pretty much exactly what is happening on hardware. Right? Unlike analog where there's always fluctuation, so software doesn't exactly represent hardware, but in this case the software and hardware almost certainly match because there's only zeros and ones. Right? Okay, now so guys, I want to introduce you to now before we finish off this evening, the last topic I want to show you is something known as a 3-state gate. There's another device. So up till now, up till this afternoon, I am showing you all the building blocks of how a rich system is made. When I say a rich circuitry is made, you know, you may want to build a calculator. You may want to build a traffic light system. You may want to build a security system. You may want to build an air conditioning control system. So all of this, or an engine control unit, right? These are all built using fundamental basic gates, right? So you need to know gates and devices, right? So you need to know, even though a decoder and a half adder, a full adder, half subtractor, full subtractor, decoder, encoder, mux, demux, all these things are higher level circuits or middle level circuits. We need to have all of this to build something which is actually of practical use, like a calculator, for example. Now, there is another last gate which I want to introduce you to. Something known as a three-state gate. All right? So three-state gate, there is a logic 0, there is a logic 1, and then the third state is high impedance. Right? Okay? Right? So the three-state gate is when you enable, right? When it is 1, right? So there's two inputs over here. Firstly, it looks like a buffer. The first thing, it looks like a buffer. In a buffer, 0 goes in, 0 goes out, 1 goes in, 1 goes out. But over here, there's a buffer and there's also an enable signal. Remember this. This is very important because the enable signal will be used in mux, demux, decoder, encoder, all these other adder, subtractor, half adder, full adder. There will always be an enable signal. So the enable signal is a generic signal which is used to basically, if you can think of it, it's like a switch to turn the gate on or turn the gate off. Even though there is a signal going in, right? It's basically you turning it on or turning it off. Like for example, you have a DVD player, right? You have a DVD player. The DVD player is connected to your TV. You put your DVD inside, you press play on the DVD player, but your TV is turned off. Your TV is off. Will you be able to see the signal? An image? No image. Right? Even though the DVD player is supplying the input to the TV, doesn't necessarily mean the TV will show you the image. So you have disabled the TV. If you turn it on, you enable the TV, and therefore you're able to watch the TV program. Alright? Or whatever your DVD was. So, same thing goes over here, same concept. You have your gate, you have an enable. So basically you're switching on and off your gate. So if your enable is off, look over here, enable 0. If your enable is 0, which is off, right? This thing here gives you Z. Z means high impedance. You don't see anything, nothing output, no output, right? Neither 0, no 1. It's no output at all. Okay? Now, if the enable is 1, well, it acts like a buffer. You put a 0 in, 0 out. 1 in, 1 out. So that's all we're trying to say over here. You have to now consider that for every gate, there is an enable line. Right? And this is especially important when you're looking at mux, demux, decoder, encoder. Because we will be building next week in your tutorial bigger circuits using small. So using 2 small decoders to build a bigger decoder. Right? Okay. Now remember, I always make the joke about bus. Bus is a set of lines over which data are transferred. Not just single line, but when you have multiple lines. Right? Like for example, if you have encoder, 8 by 3 encoder, so 8 lines going into the encoder, that's a bus. Right? That's a bus. Okay? Data might travel in one direction or data might travel in both directions. So these are some things. Now, guys, I won't be covering this right now, but this is the concept of how RAM is made. RAM and ROM are made. RAM stands for random access memory, and ROM stands for read-only memory. All right? Okay. Now, basically, using your encoder and decoder, right? This is not, we're not actually covering this, but I want to give you an insight into how these things work. So remember what I said, what is one application of a encoder and decoder? You select certain memory, certain areas of memory. So you put the address in, so let's say you say 110, address 6, so memory number 6 has to go on. Right? So that's how this particular system works. And we will look at this later on in the semester if we get time. So for now, out of interest, we will stop over here, guys. Designing of ROM. Designing of ROM is only for your interest only. Okay? For your interest. Designing of ROM. Alright? Now, from Monday, from next week, from week 9, we will now change gears. We will now move into another phase of the course. Up till now, you were looking at something known as combinational logic. Combinational logic means you flip the switches over here and the outputs change. Now, from week 9 all the way till week 13, and that's where your project will be based, your project will come out from this topic, we will be looking at something known as sequential logic. How to build memory. I was talking about ROM and RAM. You can't have a calculator, you can't have a traffic light system, you can't have most of the systems without memory. Even if you have an MP3 music player, even if you have your mobile phone to store your girlfriend's number, right? You still need memory. Your system has to have memory. How to store the bit? Where does it get stored? Now we will be moving more heavy into digital electronics. So I am pleading with you, do not skip lectures, and please encourage your friends to attend the lectures. We're going to move fast, because remember, it's a 13-week semester, not 14 weeks. So we're going to compress about 6 weeks worth of work into 5 weeks. All right? And your project, which is worth 20%, will come from sequential logic. So please be here and please attend all the lectures. All right? Okay, thank you. We'll see you on Tuesday. Oh, and I think there's some labs tomorrow, right? Yeah, okay. Thank you.